Hey, can you hear me? Okay.
Right.
Hi, I'm Dan Popescu. I'm an SRE in Adobe, and I'm joined today by Constantin Muraro, a colleague of mine. And we're gonna tackle the topic of deploying real-time apps on thousands of servers with no headaches, let's say. A bit of context. We work for Adobe Audience Manager, which is a core component of Adobe Experience Cloud, which allows you to create unique audience profiles and then identify segments, like important segments for your audience, and then use those on any digital channels. So basically, it allows you to understand your audience by combining data from multiple sources. And today we're going to focus more on the edge component, which is responsible for real-time data manipulation. So let's move forward. We've talked about, so the topic tackles the deployment aspect of real-time applications, but we had to overcome a lot of challenges to be able to have an easy-to-use deployment platform while transitioning to a unified on-call schema. So in the past, we used to have SREs performing all sorts of, like, most of the operational tasks. But now we wanted to also involve the engineering teams. But they had to have an easy-to-use platform to just jump right into the deployment aspect of the applications. While we also wanted to reduce the operational burden. So we wanted basically easy-to-use interface that you can click and just deploy your applications on a large number of servers on multiple geographical regions. And here you can see a typical deployment model for pipeline. In our case, we were used to deploy some servers to stage environment, then some canaries in prod on multiple regions, and then if everything perform a lot of validations and if everything is okay, then we used to have a rollout deployment window. But this procedure lasted like hours, 4 or 5, even more, when we were talking about thousands of servers. And we will see how we fix this issue.
All right. So regarding the deployment part, we are concentrating more on the real-time services, which is basically our set of micro and macro services that we have inside Audience Manager. These are basically web apps that receive a lot of HTTP requests from our clients. For instance, if you go to a given website, the client might want to create a digital profile for you, even if you are authenticated or unauthenticated. And to that end, it will integrate with Adobe Audience Manager, basically have a JavaScript library if it's a website, or an SDK if it's a mobile app, that will make calls to our web services. The main web service is the data collection service, which we'll discuss a bit and see how we tackle deployments for that service. But there are a lot of other, streaming services that we use to pass the data from the edge, which is the project that we are working on, back to the Keystone, which is our main data center, where we have this big edge-based data store with a ton of MapReduce jobs on top of that, and also the export part, which is basically outbounding data to the customer, back to the customers, or to other partners. So, to sum up, the edge architecture is comprised of this main web app, which is called DCS. It has multi-region deployment. So basically, we have it deployed on a few hundreds of servers in 8 regions. It's deployed in AWS. So we try to leverage as many services as possible from there. That includes S3 for data storage. Also, we are looking for Kinesis to stream the data, and SQS for message passing and all that. The application itself is quite old. It has I think 11 years, so it doesn't yet have the microservice aspect of it. It's more like a monolith. that historically was very hard to deploy. And what we did in the past, maybe you might be familiar with, for some of you guys, what we did in the past was basically, because it was so hard to deploy, we basically delayed that deployment part. So we deploy like every 1 month or 2 months. But that meant we were introducing a lot of code changes in a given deployment. So if something went wrong, that meant it was hard to debug and see what was the actual code change that introduced that problem. The main issues that we are seeing and we are trying to look at is the number of errors that this web app generates, the request time, because we have SLAs for our customers, but also if the request time increases, that means we need to add more servers to process the same amount of requests. So there are a few key metrics that we look at whenever we deploy a new application, and what we want to do is basically the way we did, like Dan mentioned earlier, the way we did deployments was basically have the infrastructure set up. Let's say we have 100 nodes in each region, and then go on each of those running servers, run some Ansible playbooks that would deploy the new version. Basically, SSH to each batch, let's say take 10 servers at a time, upgrade the application, apply the new configuration changes, restart application, and move to the next batch. So basically that would be run as an Ansible playbook from a developer's laptop, which has a set of issues. For instance, the laptop might die, right? It might run out of battery, or you might lose connection, or you might have problems with the SSH connection, the limits, and so forth. Also, it was very hard to audit this. It was also very stressful for the developer because they had to actually stay there for 5 or 6 hours till the Ansible playbook finished. So these are the issues that we try to eliminate and move to something that was more automated and more reliable. To that end, we looked at some open source solutions. One of them is Spinnaker, which was actually developed by Netflix and Google, and it was a very easy to use tool for us because it allowed us to take this existing application, perform little to no changes to the actual app, and deploy it using Spinnaker. So what Spinnaker is a set of microservices that you can run. You can even run it now in Kubernetes. It's very easy to set up. What we did 2 years ago when we started this, we actually deployed it in Amazon using VMs, virtual machines. It was a bit more cumbersome. But right now with Kubernetes, I think it takes like 10 minutes to set it up. So what Spinnaker allows us to do is 2 things. One is to have what the basic principle behind it is the immutable infrastructure part. So that means instead of going to the existing servers and applying changes there, existing production servers, right? And applying changes while those servers are running and possibly introducing some errors there, some issues. Instead of doing that in place, whenever you want to deploy a new app, you spin up a whole new cluster, or a whole new fleet of servers using your new app. So basically, at any given time when you do a deployment, you have the old stable version, let's say 100 servers for a given region, and then you create a new server group alongside that, a new autoscale group for AWS, but it has support for other cloud providers as well. And you run the new version, and the secret sauce here is the fact that you put both these clusters under the same load balancer. So, for instance, let's say you have the old cluster with 98 servers. You create a new cluster with 2 servers, let's say these Canary deployments. Now you have a total of 100 servers, 98 with the old version, 2 with the new version. Put them all under the load balancer, which means that the new version will receive 2% of the traffic. So if something is wrong with the new version, let's say you introduce a code change that is misbehaving, you are only impacting a small fraction of the traffic. And the whole idea here is to limit the blast radius whenever you introduce a code change. So basically, what Spinnaker allows you to do, it offers this deployment strategy out of the box. Basically, this Canary deployment or the red-black deployment. And the idea here in Spinnaker, the way it works in Spinnaker is basically you create a pipeline. I don't know, how many of you heard of Spinnaker? All right, and Jenkins? All right. So you can think about it as a Jenkins pipeline, but it's the continuation of the Jenkins pipeline. So you have the Jenkins pipeline that takes your code, builds it, compiles it, and creates an artifact, be that a jar file, an RPM, a Debian file, or Docker image. And after that, you feed that into Spinnaker and say, hey, OK, I have this artifact. I want to deploy it. I want to deploy it in a given cloud provider. It might be AWS, it might be Kubernetes, it might be another cloud provider. And I want to have this deployment strategy. If it's a Docker image, things are pretty straightforward. But things are getting more complicated if you have something like an RPM or a Debian for a Linux file, or even a jar or an archive. So for instance, in our case, where we deploy in AWS, we have basically RPM packages containing our application. And what we do in Spinnaker, we have this pipeline that says, OK, whenever the Jenkins job has finished and has created that RPM, it will publish it into an repository. It might be bin tray, it might be Artifactory. Once it's there, we have Spinnaker run the pipeline that says, OK, I want to spin up a box, install the application, make all the changes that I want to do to that application, be that that can include apply the configuration, call any other services that I want to call to fetch some data. And after the application is set up, I want to do a snapshot. I do a snapshot and create an image, which is basically a big file that we store in S3 in the cloud. And once the image there, which is for Amazon, it's an AMI, Amazon image. Once the image is there, or you can think of it as an ISO file, right? Or a file that you have on a CD when you install the OS. But this one is a file that also contains the OS and the application. So we have this image, and then we have the second stage, which is the deployment part, where we can take this image, which contains the application which is fully set up, and deploy it on a number of servers. It can be one server, or it can be 1,000 servers. But the nice thing about it is the fact that it should be consistent across this fleet of servers that we are going to deploy. These are new servers that we are spinning up. Yeah, and another thing is, because we are doing all this from Spinnaker, which also has an UI, also has an API which we can call from Jenkins, we are no longer using the developer's laptop, which means we can also have audit and logging and all that.
OK, so Kosti mentioned that we basically adopted the immutable infrastructure concept, let's say. So for this, we had to start baking our EMIs. We chose a multi-layer approach. Basically, we started first building our base EMI. This image contains all the common software which is shared between servers. This can contain things like, I don't know, the SSH config for instances, or the node exporter for Prometheus, or the metrics client, and so on. And we bake this base EMI, we save it in AWS, and we use this as a base image on top of which we bake the application EMI, which is application-specific configurations. We also perform configuration management for all the applications within the EMI, so that when we deploy this image, no changes are performed on the actual servers. During the bake process, we also fetch secrets. So whenever we need to store secrets on the actual production servers, we basically burn them in the image, and thus reducing the API calls to other external services once the machine is started. And we also perform kernel and OS patching. This is especially important when you're consider the fact that sometimes you need to patch your servers for known vulnerabilities, and you have to do them fast. So we usually patch the EMIs, and then on the next deployment window, we just deploy all the fixes. And then once we have the application EMI, this is copied across all of our AWS region and used to deploy. Once the instance is started, so the instance uses the pre-baked application EMI, we need to provision the instance. So basically start all the services on it, but also we need to do some extra configurations, such as setting up the host name or mounting and formatting the disks, which are not available when you're baking the EMI with Packer. This tool is an internal build tool, so it's a Java application. And it leverages the Autoscale Group Lifecycle Hooks. These are basically some small apps provided by the Autoscale Group in AWS, which allows you to take some actions when the instance is in a specific state, when it's starting or shutting down. So we leverage those lifecycle hooks, and based on those, we provision our machine. This means we start all the services and we validate that everything is okay.
Yeah, and for your application, if there are two cases, right? If it's a stateless application, whenever you switch to the new version, you can just shut down the old server fleet and be done with it, as long as you have removed it from the load balancer. However, what happens when the application is service stateful? In our case, the main application, the DCS, is stateful in the sense that it keeps some temporary data on disk for like 5 or 10 minutes before pushing it or streaming it back to our backend. So because of that, we can't just shut it down automatically. We need to have this custom logic that says, okay, before shutting down this old server, I want to make sure that I pushed the data to the backend before power it off. To that extent, we have created a simple application that integrates with a nice feature from AWS called Lifecycle Hooks. So basically, the Autoscale Group in AWS, which contains all the servers in a given cluster, gives you this feature where it can it can send a signal to you whenever a server is about to get terminated. So what we do, we have this application, which is a Java daemon app that runs alongside the main app on each server. So this app is running there and listening for this signal from the Autoscale group that says, hey, this is about to get terminated. When this app called Shredder receives this signal, it will run the shutdown logic. In our case, basically upload some data to S3 or push some data to Kinesis or whatever logic you want to have. After the shutdown script gets executed, Shredder will send the signal back to the Autoscale group that says, okay, I have done my shutdown logic. You can terminate this instance. So basically, it will send this shutdown complete event to the Autoscale group. When that happens, the box will get terminated. So to recap here, the workflow, the deployment workflow, we have the baking stage that Dan mentioned, basically spinning up one server that will use to basically create our application, basically install the RPM, install the Debian file, or run Puppet if you want Chef or whatever you want to do there. Then do a snapshot. If everything is okay, you'll have this snapshot that you can deploy on multiple servers. So you then proceed to the deployment phase, where you have the old cluster, you deploy a new cluster, then switch the traffic to the new cluster from the load balancer. The old cluster will not have any more traffic. You can decommission it, and then you can choose here to either use something like a lifecycle hook to make the cleanup, or if it's a stateless app, you can just shut it down and be done with it. One important aspect here is what happens in case of a failure. What happens in case of a failure with a new version that you detect a bit later? Let's say you have 100 nodes with the old version, 100 nodes with the new version. You switch the traffic to the new version, and then after a couple of hours, you see an increase in the number of errors. Obviously, you would like to roll back as soon as possible to the old stable version. To that end, you can have the old version still being up and run in parallel both clusters. It obviously means you are paying double the money, right? You have 100 nodes with the old version, 100 nodes with the new version. But it might be something that you might be willing to pay for a few hours until you see that everything is okay with the new version. Or if you wanna limit the cost, you can remove the servers from the old cluster, so be 0 and 100. If you detect an issue, then you can switch to the old cluster by spinning up from the old image, but that might take a few more minutes. If you have the old cluster running, switching to that one, it takes, just a switch in the load balancer, it takes like 30 seconds to do it. If you have decommissioned the old cluster, you need to spin up the servers. which might take 10 minutes or 20 minutes. So it might be something to think about it. Yeah. All right, so in terms of provisioning the DCS instance, we start with the DCS image, which we baked. This contains the application, contains the configuration, contains basically for DCS we are running Puppet. So basically we are running Puppet with a masterless approach, which configures the system to our liking, where we have the application, the configuration, we have actually multiple applications that we are configuring. And basically this is one server with a few services running on it. What we do with the init script that we have, the instance provisioning script that we have, we basically add Bootstrap. We configure each service to pick the right configuration for that specific region if we have multiple regions, and do some validations to see that everything is set up okay. And also for DCS, we do a warm-up where we basically generate some synthetic requests to that server to basically warm it up before receiving the production traffic. This is happening at instance bootstrapping, right? So if you have the image and then you try to deploy it on 1,000 servers, you want to limit the amount of operations that you do at bootstrapping. Because, for instance, if you are calling an external service at bootstrapping and you have 1,000 servers that is calling Route 53, or is calling the Puppet Master, or is calling another service, if that service is down, you are not going to be able to spin up that server. So basically, we are trying to move all that logic to the bake part. So bake part basically spin up one instance. If everything is okay, then I'm 100% sure that I can deploy to 1,000 servers. So move that all to the bake phase, and then at the deployment phase, try to limit the amount of external services as much as possible. In our case, it was not possible to remove all of these calls. We still do one call to Route 53 to basically register the DNS entry, but that's about it. All the rest that we are doing is basically set up the disks, which is a local operation, which might still fail, and basically warm up DCS, which basically generates some requests. Okay. So let's see Spinnaker in action.
We have a small movie. So this is a scale-up procedure, basically in which we've bootstrapped 500 servers. Each of those green boxes represent a single instance. Those are really powerful machines. So each of those green boxes is a C3 large instance, which has 32 cores and 60 gigs of RAM, if I'm not mistaken. And during this phase, the provision takes care of bootstrapping the instances. And once all of them turn green, it means that they are ready to receive traffic. And we have the reverse procedure as well.
And to move to the next slide.
The reverse procedure, in which you need to scale in your infrastructure, but because in this specific scenario we're talking about the stateful application, we have the shredder that Costi mentioned, which takes care of actually cleaning up the instance before shutting down the actual server. So in which case we don't lose any critical data. So basically a scale to 500 instances and then a scale to one instance. Scale that one.
So basically this is an example of a pipeline in Spinnaker. It's pretty much free form. You can basically create a pipeline that has a series of stages that you can combine however you like. It does have a set of pre-built stage types. For instance, the bake part, which might be something for CentOS, or might be something for Ubuntu, or it might be something for Kubernetes or Docker. It also has check type deployment stage, manual validation stage, and all that. What we see here is basically we assume that the image was baked in another pipeline. So the first stage there that you are seeing is the finding the AMI that was pre-built. So basically this is doing a lookup in AWS that says I want to find the latest DCS AMI, the latest image. Once we find that image, we can basically deploy on a number of regions. What we are doing here is basically we are deploying canaries in each region, and you can select which region to deploy to. For instance, right now, for this deployment, we only deploy to Tokyo. So basically what this does is find the AMI and then deploy 2 canaries in the Tokyo region. So basically spinning up a new server group, a new autoscale group with just 2 servers in that region. After that, what we are doing is basically monitoring that canary. Right now, we are doing that manually in the sense that we are looking Grafana and checking some dashboards, look at the number of errors, look at the request time, compare that with the old stable version. But the nice thing about Spinnaker is the fact that it added half a year, 6 months ago, a new feature, a new service called Automatic Canary Analysis, which does that automatically. It basically allows you to fetch some metrics from Prometheus or Graphite or other metric source, specify the metric name that you want to look at, specify some thresholds, and it will take care of monitoring those metrics. And if everything is okay with the canary, it will proceed with the full deployment. Right now, for us, it's a manual judgment part where we deploy the canary, we look at the dashboards, and then click proceed, and then we scale up the new server to 100 servers and decommission the old one. So what we are seeing here is the later part of the process where we are scaling down the old fleet, the old server fleet, after we make sure that the new version is behaving okay. So the achievements that we had with moving to this approach, basically the most important thing was the deployment time. Like we mentioned earlier, for running those Ansible playbooks from the developer's laptop, it took a lot of time. It was error-prone. It didn't ensure consistency because if you are running SSH commands on 100 nodes, you might have some errors on one of those servers or 2 of those servers. And by moving to this new approach, the deployment time decreased dramatically, but also it allows us to have quick rollbacks with the approach that we mentioned earlier, because we have 2 servers and we don't have just one that we are upgrading in place. Because we have 2, we can quickly roll back to it. It takes very little time. We have consistency, and also very important, the way we had it earlier, where we have one cluster of servers that you are upgrading in place. That meant that those servers were running 24/7. So basically, if you want to upgrade the OS, you have to reboot it, right? If you want to change the instance type, then you have to create a whole new cluster, right? And you might have to use Terraform, Troposphere, or CloudFormation, or other solutions. With this new approach, basically at each deployment, we are free to change the instance type, we are free to change the OS, we are free to basically upgrade and experiment with different instance type in this case, which basically allowed us to find a new instance type that was actually more performant for the class of applications that we are running, and we were actually able to have a 30% performance increase just by changing the instance type. But to find the right instance type, we actually had to do like 5 or 6 deployments, trying out multiple instance types under real production traffic, right? Under real load. So basically, Spinnaker allowed us to basically, at deployment phase, to choose the instance type.
Okay. Costi talked about DCS, the data collection system app, that we've moved to Spinnaker. But we also have Iris, which is another Java application. This time we are talking about a stateless application, so no critical data is stored on the instance itself. We used to have around 2.5K instances spread across 7 regions, so a large number of machines. And in the peak times, we used to have around 700,000 HTTP requests per second. Managing deployments on this kind of infrastructure was really difficult, in our case at least. Once we moved to Spinnaker, the deployment part looks pretty simple. So we bake a single EMI in a single region. Then we use that EMI to deploy across all of our partners, so across all of our regions. And since this is a stateless application, we don't care about data which is stored on the disk itself. So right now, when we are performing Iris deployments on top of Spinnaker with the immutable infrastructure mindset, we're deploying in less than 10 minutes for 200 instances, because it was easy for us to go to higher spec instance types to change the OS in a single deployment window. And we ended up lower the cost by 78%. So if before it was also almost impossible to perform deployments on Iris without actually affecting the application itself, on 2,500 instances was really, really difficult. But right now with Spinnaker, this is a trivial operation.
Okay, so in terms of the lessons learned about using Spinnaker, after using Spinnaker, so the main idea for us was to stop SSHing, to start authenticating on each server and do something more smart. For instance, it's the same idea with Kubernetes, right? You don't authenticate on a container. You basically have the Docker image and you say, I want to have 1,000 containers with this Docker image. It was the same thing for us, but with virtual machines, where instead of SSHing to each node running Ansible playbooks and all that, we want to have an image that we deploy to 1,000 servers. To that end, we did encounter a series of issues with this approach. Basically, the thing that we mentioned earlier, if we have at instance bootstrap, basically whenever you spin up 1,000 servers, if you have that init script calling external services, it was error prone because the external service might have a rate limit or it might be down. For instance, if you are calling, if you are fetching the package, the RPM or the Debian file from an Artifactory or from bin tray, that might be down, it might be slow. So you want to move that to the bake part. Another thing was setting up Spinnaker itself, the thing that I mentioned at the beginning of the session. In our case, we had to use CentOS. Basically, Spinnaker was more or less built for Ubuntu, so we had to create RPM packages for CentOS. It was a pain to do it. It was also very hard to create all the setup in AWS to basically allow Spinnaker access to deploy to our AWS accounts. So basically creating all those IAM policies was a bit hard. Like I mentioned earlier, things are starting to get better because with the migration to Kubernetes, even if you are not deploying to Kubernetes, but just have Spinnaker run on Kubernetes, on a small Kubernetes cluster, it will save you a lot of effort. Things should be a lot easier in that regard. Also, the documentation is getting better for Spinnaker. It has quite an active community. We are actually trying to contribute to it, but we are not. Adobe is not the main contributor. Like I mentioned, it's Netflix and Google. But I would strongly recommend it for deployment. Deploying your applications. Also, it has Spinnaker has a Redis cluster that it caches data to. Basically, it fetches the data from AWS or the other cloud provider and uses Redis to store that as a cache so that it doesn't call AWS every single time. To that end, we are using Elasticache from AWS, and we did encounter issues where it was under-provisioned, so we had to actually have this strong Redis server for Spinnaker to be okay with it.
So this is our current state. Right now, our data collection system auto-scales by itself. So based on the traffic pattern, we scale up or scale in the infrastructure, and this is done using auto-scale policies. So basically, we monitor the number of requests or the load on the servers, and based on that, we can easily scale the infrastructure up or down. So right now, both SREs and engineers are performing day-to-day operational tasks. So we migrated to a unified on-call schema. We also have been using lately Spinnaker in a multi-Kubernetes cluster setup. So we hook Spinnaker across multiple Kubernetes clusters, and from a single UI, you can deploy your app easily on different AWS accounts or in different regions, but also on different cloud providers. So right now we are experimenting deploying applications in both AWS and Azure using Spinnaker and the Immutable Infrastructure concept. And a lot of projects within Adobe have started using Spinnaker for their deployments. That's about it. So here is our contact information in case you want to find out more. The EC2 shredder, which we've open sourced, can be taken from our GitHub repo. So in case you have any questions, now is the time to ask them. No.
All right. Be sure to also rate the session if you found it helpful. And thank you so much for having us today.
Thank you.